All right, we're back. We are doing Calc AB Notes 24. We're going to be on page 6. I noticed when I reviewed the video last time that at the end of the video for page 5, just the iPad wasn't there. And so I ran a security update on my computer. My computer was working great prior to that. And then as with a lot of updates, things aren't going so well for me now. So sometimes when I'm using the recording software here, I'm just basically in a meeting with myself on Zoom. Sometimes when I switch back and forth between things now, it's not picking up in the recording what I'm seeing on my screen. I don't really know how to solve that. Hopefully it just works itself out with like a patch or something. I don't know. Anyway, on the last one, I had accidentally, in part C, I had substituted 1/2 instead of -1/2 for into arcsine, so I should have had a -π/6 there. I don't remember if I made a mistake on D. I know I made a colossal mistake on D while doing the video, but that part was recorded, so everyone gets to see that. Anyway, if you missed it last time, this should clear that up, hopefully. All right, let's take a look at this. So we are going to use differential equations to model situations, right? Situations where things are growing over time or shrinking over time. But changing over time, I guess, is what I should really have said. You need to be able to read a scenario and come up with a differential equation for it, which is never as bad as it like initially seems like it might be. So let's take a look at this. We have a rumor spreads among a population of n people. So we have a population of n people, and what's going to happen is it's at a rate proportional to the product. So let me say a word about proportional. So a rate proportional, as far as AP calculus is concerned, the only sort of proportionality that exists is directly proportional, which means it will always be k times something. So inversely proportional doesn't really exist. Instead of saying inversely proportional, a problem would say directly proportional to the reciprocal of. So you only need to worry about directly proportional. So a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. If P represents the people who have, okay, so a lot of information there. It's the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. So that's something we're going to want to work out. So N is the total population. If P represents the number of people who know the rumor or who have heard it. So I feel like at this point, I'm just like killing it by highlighting everything. But you know, we're gonna use these things. So write a differential equation used to model this situation with respect to time. Okay, so time is our independent variable here. So, all right, so the rate of change of people, model the situation. So it's a product, a rumor spreads among a population of n people. All right, so P is the number of people who have heard it. So I'm gonna say that dp dt is what we're looking for. We're looking for the rate of change of the proportion of people who know this. So dp dt is going to be directly proportional, so k times. So maybe I should, I don't exactly know with this color coding that I've done here. I don't know how to put that into play here. So rate proportional. I also don't know what color I use for that. I think I use this. So this is from that fact. And then, all right, so it's the product of the number of people who have heard the rumor, which is P. That's the number of people who have heard the rumor. So this will be maybe, let me see here. I don't think I'm gonna be able to pull this off. It's too many colors. I went too crazy with it. P, so that's the number of people who have heard the rumor, times the number of people who have not heard the rumor. If P is the number of people who have heard it, so then I'm gonna multiply this. So I think it'll be N minus P. This is one of those things where I'm like, oh, coloring it in would be a good idea, and then I'm really regretting that. I think this is all the information that we have. So directly proportional, so K, to the product of the people who have heard the rumor, which is P, and the number who haven't. So if there are N people in the population and P people have heard it, then N minus P have not heard the rumor. I think this is our differential equation. So I'm going to say this is it. And I don't know that there's necessarily a better way to highlight that. So I'm going to say that's it. So there are n people in the population, proportion. Yeah, I think that does it. This you'll find out later in life is the logistic differential equation. Doesn't matter to us right now, but it is. So this is a logistic differential equation. And later, if you're in Calc BC, you'll learn how to solve this. In Calc 2, you'll learn how to solve it. You need to know how to do partial fraction decomposition before you can do it, which in Calc AB, in my class, you'll learn at the end of the year. So at the end of the year, you would potentially be able to solve this if you wanted to. All right, let's see. So the next thing we're going to talk about is something that you've probably dealt with before. It's those exponential growth and decay problems that you do in Algebra 2. That model is a very nice separable differential equation. So it's really common to see it. And I'm aware that in these notes, there's not enough space to deal with all of the things that are involved here. But, so this is what we're dealing with. A quantity that grows. So this should be in like its own box. I don't really know why it's not. So a quantity that grows at a rate proportional to the amount of the quantity currently present is said to have an exponential growth model. Okay, and we can write a differential equation for that. So it's growing, think about it, it's growing at a rate proportional to the amount that we currently have. So the rate of change of y, right? So the rate of change of y is directly proportional to the amount that you currently have. So dy dt, the rate of change of y with respect to time, is directly proportional, k times the amount you currently have, k times y. So this is an exponential growth model, and you're gonna need to know it. You use this kind of all the time. So k is called the growth constant or relative growth rate. It's really the rate of change of y divided by y, which, you know, like just take this differential equation, divide both sides by y, and you get dy dt divided by y. That's fine. Usually you're given k. If not, you're given enough information to solve for k. So there's actually a really specific solution to this. So I'm going to solve it in this tiny little space here. And what I'm going to do is I will separate. So k dt. I will integrate. And then this will give me the natural log of the absolute value of y is equal to kt plus c. And this will give me, we skip a bunch of things, y is equal to ce to the kt. Often you see that as a, often you see it as p equals, a equals pe to the rt, pert, right? You'll hear people talk about that. And then depending on how old they are, they'll talk about like shampoo or something. So this is the general solution. But if we know this piece of information, that our initial condition, that y of 0 is equal to y0, we can solve, right? And so if you plug in 0 for t, you get e to the 0, which is 1. So that means that c is actually just y sub 0, which is like a weird thing that you do often. If you don't know what the specific value is, you just say that at t equals 0, you get y0, or at t equals 0, you get b sub 0. Whatever the independent variable is, you just say it's like that sub 0. The dependent variable, sorry, not the independent variable. And I'm going to take this up here and just write my solution. So this y equals y sub 0 e to the kt. So you can memorize that solution. I recommend that you do. But additionally, you should be able to do it. So make sure you can actually get it. So every time I solve this, I'm going to actually go through the process. Let's see if we can do this. So what do we got going on? Suppose an initial population of 10,000 bacteria. So an initial population of 10,000 bacteria, that's your initial value, right? So that's B of 0, B for bacteria, is equal to 10,000. Okay. Grows at a rate of 2.5% per hour. So that is going to be our K value. Grows. It's important that it grows. If it decreased at 2.5% per hour, then it would be negative. But in this case, I'm going to say that K is equal to 0.2, what is it? 0.025, 2.5%, but we want it as a decimal. So, well, that is a decimal, but you know, we want it per 100, not 2.5. So we have this. B of T is the number of bacteria. All right, so the rate of change, it grows at a rate 2.5% per hour, which means you need to know how much you currently have to know how much it'll grow. So it's growing at a rate that's directly proportional to the amount you currently have. So our differential equation is dB dt equals K, or 0.025, times B, times the current amount. Because if B increases, the rate of change will increase because it's always 0.025. I really want it to be 0.25. 0.025 times B. So if B increases, the rate of change increases. As B goes to infinity, the rate of change goes to infinity. It's a pretty crazy situation, actually. So this, I think, is all that we need, right? So our actual solution to this problem, I would say, is, I'm looking for like something I didn't already highlight with, this and this. So we have a differential equation and we have an initial condition. That's all you really need. So this is our thing. And now we're going to solve it. So dB dt equals 0.025b, which means dB over b is equal to 0.025 dt, which is really common, that you just end up with a constant times dt or a constant times dx, constant times d independent variable. So this will give me natural log of the absolute value of b. So I like to solve this just for practice, really. I like you to solve it for practice. I think I'm probably okay in my life. I think I don't really need to practice these all that much anymore. I mean, I'm going to keep doing it, but so then I would get b equals a new value of c e to the 0.025t. And then I would use the initial condition up here, that b of 0 is 1,000, and solve for c. So b is 10,000, actually. 10,000 e to the 0.025t. So this would be my answer to the initial value problem. So you get a function. B is a function of t. Now these next two problems are really like algebra 2 type problems. Been having a lot of trouble going back and forth between the calculator and the iPad. So what I'm going to do, I'm going to solve these by hand, and then use the calculator to get approximations. Then I'm going to try to fill them in on the notes. Hopefully you'll be able to see it. I don't know. How long does it take for the population to double? Okay, so a weird thing about this is that it doesn't actually matter what the population currently is, just so long as you start with like a population of p and you end with a population of 2p. So since I know that at t equals 0, the population is 10,000, I'm just going to figure out how long it takes to become 20,000. And it will actually take the same amount of time to go from 10 to 20 as it does to go from 20 to 40 and 40 to 80. The doubling time is always the same, and you will see why as we do this. So I'm going to say that if you have 10,000 to begin with, then you'll have 20,000 when it doubles. Okay, so if I start solving this, my first step is actually why it doesn't matter what the values were. 20,000 divided by 10,000 is 2. So if I had 25,000 to begin with, I would have 50,000, but 50,000 divided by 25,000 is 2. This number here will always be 2 for doubling time, and that's why it's going to come out like that. So this 0.025t is equal to the natural log of 2. Take natural log of both sides to get that exponent down. And then, so t is going to be exactly the natural log of 2 divided by 0.025. I'll use a calculator in a second. I'm just afraid I won't be able to get back to the notes if I do it. Like, I'll be able to, but you won't be able to see them. And what good is that? How long before the population reaches 60,000? This is like almost the exact same problem. So you get 10,000 e to the 0.025t. I feel like I keep saying 10,000. Is that right? Yeah, 10,000. Okay. It just seems like a lot, but also in the context of bacteria, maybe not a lot. I don't really know what a reasonable number of bacteria is. Okay, so divide. You start to get this sense actually. So like now it's going to be 60,000 divided by 10, right? So what if it went to 100,000? Be 100,000 divided by 10,000, and it just keeps working out that you just keep getting like the ratio on the right hand side. So this will just be 6. If it was 150,000, it would just be 15. And you just keep doing that. So 0.025 t is the natural log of 6. So t is approximately the natural log. No, it's actually not. It's exactly the natural log of 6 divided by 0.025. Now, what that is as a decimal, let's go to the calculator and try to find out. So I'm going to switch over to the calculator. And then this is where, in the last video, it all went wrong in a number of ways. It went wrong because I realized I had done it wrong, so that wasn't great. And then also, so what can I do? I'm going to solve, DE solve. Let's say b prime equals 0.025b, and b of 0. That's it. It's definitely the inspire that does it. Let's see if it comes back. Yeah, b of 0 equals 10,000, where t is the independent variable and b is the dependent variable. Okay, so I get this. This is probably 0.025. There you go. So it's equivalent. It's just that the calculator prefers it a different way. Let's figure out what the natural log of 2 divided by 0.025 is. And then let's figure out what the natural log of 6 divided by 0.025 is. Okay, so these are the values. I'd like to play around with this more, but I'm hoping that I'm able to get back to the notes to actually show them to you again one more time, but we'll see. Let me just jot these down. 27.726. That's in years. And then this is 71 point. That's not in years. That's in hours. Oh my God. That's crazier by like a lot. So hours, and then 71 point. I mean, the year thing didn't even strike me as all that weird until I realized it was bacteria. Bacteria grow incredibly fast. I'm trying to go back to the iPad. Hopefully the video picks this up. It didn't the last time. That was incredibly frustrating. Not pictured in any videos, like 8 hours of me trying to solve that problem. All right, so these are the answers that I've gotten. I'm gonna wrap this up here. Hopefully it all worked out. We'll see, I guess, or you'll see, because I'm probably not gonna watch the video. But anyway, I hope you found this helpful. I'll be back in the next video to do more of this. So I will see you there.